Today we'll talk about sensors. So sensor is a is a electrical system which converts a physical quantity to be measured into a voltage. Some examples of physical quantities we like to measure are position, sound, temperature, pressure, vibration, acceleration. So a sensor usually has what is known as the transducer, which is the active element of the sensor. And through this next two lectures and perhaps three, we will talk about different types of things we need to measure. So we'll first start with position and speed measurements, and then move on to force, strain, what else, acceleration, and so on. So some examples of position measurement. So position is basically the location, the physical location of an object from the sensor. We have proximity sensors, which basically only tell you whether something is close or not. So it won't really tell you the distance. If you want the distance, like a value, then you want to probably use a potentiometer. They can be linear or rotary, or you can use a linear variable differential transformer, which is also abbreviated as LVDT. That's what people know it better than the abbreviated form. This one measures the linear displacement. And then, of course, we have encoders, which people have probably used in some way or the other. They are basically used to measure the angle turned by the shaft of a motor. If you want speed, then one way of getting speed is to take the position data, which comes from one of these three sensors, and then do finite difference. Now, when you do finite difference, which is basically doing d p dt, so there'll be P2 minus P1 divided by T2 minus T1. This process tends to be noisy. And so if you do this, you'll see that the measurements don't really look smooth. They look all over the place. And in order to use this data, you need to take this noisy data, pass it through a filter, and then you have smooth data, which can be used for your purposes. Now, for filtering, we have various ways to filter. One is we can use a hardware filter. That would be an example, would be the RC filter we talked about in this class. Or we could use a software filter. This would be taking the data into the program and then trying to remove the noisy components. So there are filters which you can use. Examples would be a Butterworth filter. There's something called a Kalman filter. The Kalman filter is a model-based filter. Butterworth filter doesn't really require a model. So there are ways to do this, and we will not get into the details of this, but that itself, filtering itself is a rather popular and important research area. And so people do PhDs on just that topic of filtering. Let's dive into the details of some of these sensors. Let's look at the proximity sensors, and I'll give you a few examples and I'll illustrate how they work. And some of these things which I'm going to talk about, you can actually incorporate them into your project if you want to. Although you spoke to me about what you want to put as your sensors, you're free to change them if you think that some of these are easier. So as I said, proximity sensors can only tell you something is close enough or not. And there are two ways I can think of doing this, using photodiode or photocell. The left-hand side shows how a photocell is used. The right side shows how a photocell is used. For a photodiode, remember it's a diode which basically changes resistance when light falls on it. So when there's no light, the resistance is very high. If the resistance is very high, then no current will flow. And then the voltage out would be 0. That's right. And then if light falls on it, then the diode conducts, which means that the voltage drop across the diode would be something which is non-zero. Typically, the voltage drop across a light emitting diode are, a photodiode are about 2 volts. So if you read 2 volts, that means that there's a light source. And we'll see how this is implemented in sense in just a bit. A photocell, on the other hand, works in the following way. When light falls on it, it basically conducts electricity, and the charge will flow, which means that the voltage will be greater than 0. The advantage of using the photocell versus the photodiode is that you don't really require a battery here, so no battery. While this one requires a battery, as you can see here. So it's ideal to have no battery because then you really don't need to keep swapping batteries. So you could put it in a remote place and it'll just work. How is this implemented? Here's how it is done. This is the sensor, which is either the photo diode or photo cell. You need a light source because both of them are triggered by light. So when the light is on, let's say through a laser, it falls on the sensor, that would produce some voltage, right? When there's light, V diode 2 volts, V out is greater than 0. So that will basically light something. So V out is greater than 0. The moment you pass an object, in this case, the object is basically going to block the light between the laser and the sensor, which means that the V out would be equal to 0. And then you can know that there's an object. That's why the light got blocked. And you can use that logic to trigger something. Okay, here is an example of how this is built, something which you can build yourself with the kit you have, probably. Hall effect sensor. This one uses the effect of magnetic field. So what's going on here is if you have a conductor, this is just a wire, and a current is passed through the wire. When a magnetic field is introduced, so this is external. Okay, so like a magnet will produce a magnetic field that's given by B. Then the effect of this current and this magnetic field, they interact to produce a voltage across the conductor. So the voltage is given by the cross product of I times B, where I is the current, B is the magnetic field. You really don't need to know anything about magnetism here. You just need to know that the phenomenon that this is called as a Hall effect. And the Hall effect can be used in the following way. You need to get a Hall effect sensor, and I'll show you what a Hall effect sensor looks like. This has 3 legs actually. One leg is connected to the ground, one leg is connected to a voltage supply, and this is the one which will be measured, P out. This is power supply. Now, what happens is the current flows because it's connected to voltage supply. The current flowing through the sensor. You need to take your object connected to a magnet. So your magnet is attached to the object. The moment you move this object connected to the magnet close to the sensor, it produces the interaction between the magnetic field B and current I, which causes the voltage out to be greater than 0, just like I have shown it here. And that's how you can measure the proximity of the object. Okay, here what's happening is you require an AC signal, so alternating current. This basically, let's say there's a current flowing through wire, and if you know when you have current flowing through a wire, it produces its own magnetic field. Okay, so you can actually play on the magnetic field intensity by wrapping the wire in certain way. So let's say it's a magnetic field, and so the current is a function of time as shown over here. Now, what you do here is you take a metallic object and get it close to the wire, and what happens is that will actually interfere with the magnetic field, produce what are known as eddy currents, and these currents basically lead to a change in the amplitude of the current. So here the amplitude was much higher because of the eddy currents. That current got distorted, and then the amplitude decreased. And the way you can detect there's an object or not is by simply measuring the amplitude of the current. Okay, so how do you implement this? To implement this, what you need to do is you need what is known as Schmidt trigger. And if we talked about Schmidt trigger, it is a device which is used to track thresholds. So in this case, the threshold is, you saw the threshold decrease, the amplitude decrease, that is tracked by the Schmidt trigger. So the inductive sensor consists of the AC input and the Schmidt trigger. And when the metal object comes, that Schmidt trigger triggers something. It produces a 0 and 1 depending on the threshold, and that goes to the microcontroller. So this is used in exits in gated communities, car exits, and traffic lights. So now let me show you how this is done in the real world.